time for the last courses. And after exact method, we have now a presentation on heuristics. And not this Kenneth come from Belgium, and he's a guy who solved a stochastic routing problem to be here today, and it is very important to note that he succeed in this way. Thank you, Kenneth.
Yes, indeed. All of my trains were delayed, so I almost missed every connection that I had to take, but in the end I made every connection because everything was delayed. So, good day, good morning, good day. I'm from Antwerpen in Belgium, which is a nice city if you want to come and visit someday. When I was listening to Angel's talk, it was very surprising to me that even though I'm going to be talking about exactly the same thing as Angel, which is to solve vehicle routing problems, if you compare our two talks, it might be as if we're from a different planet where they speak a completely different language. Because Angel, of course, is coming at the problem of designing methods for vehicle routing problems from the side of exact methods. And I'm coming from the side of heuristics. And there's a very big divide between those two areas. So the language I'm going to be using is completely different. I'm not talking about facets or valid inequalities or all the other difficult words that Angel was using. In a sense, if you approach the problem from the heuristic side, it's, at least to me, somehow more intuitive. And also, in terms of implementation, is easier. It's not so mathematically complicated as the exact methods that Angel is developing, even though they sometimes result in heuristic methods. Right? For me, that's very interesting to see that you can have a single problem, and in our field we tackle it from both sides, exact methods and heuristics. We both may arrive at a heuristic for our problem, but the design is completely different. That's, to me, is a very fascinating thing, and I think we see both sides also coming together in math heuristics, etc. So I think it's good to have these both presentations back to back so you can compare and see which method suits you better. Let me start by asking you a question. Who has developed a heuristic or a meta-heuristic so far? Just raise your hand. Yeah, okay. A lot of people, I would say small majority. Let me pick a random victim. Yeah, don't worry. With the curly hair. How did you do that? What kind of methodology did you use to design the meta-heuristic that you use? Yeah, okay. Yeah, so you started from something that you knew maybe, some kind, or that you thought was interesting, some kind of framework, and then you added stuff to it until it worked. Yeah. Did somebody else use a different methodology? You used what is no doubt the most successful methodology to develop a heuristic. I would call it iterated hacking. You take something you know, you implement it, and then you add stuff until it works. All right. So this talk is about some research that we did in which we try to be a little bit more systematic about that. And I've called it the modern way to design a heuristic or a meta-heuristic. What is a heuristic, by the way? What is a meta-heuristic? What's the difference? Let's be clear about that from the start. Anybody want to have a shot? Yeah? A meta-heuristic combines different techniques. Is that what you said? Yeah, not sure I completely agree with that. I would say some heuristics also combine many different ideas. Yes?
Basically, heuristic is successful for we escape from local optimal instead of heuristics.
So if you have a heuristic, it will never attempt to escape from a local optimum. So, you know? Yeah? Yeah, okay. I think that is closer to the idea that I have of heuristics versus meta-heuristics. I would say a heuristic is an algorithm that is not an exact method. So a heuristic is an algorithm that gives you no guarantee that you will reach the optimal solution in a finite amount of time. So you'd have two types of optimization methods. On the one side, you have exact algorithms that come with a guarantee to find the optimal solution. On the other side, you have heuristics that don't have that guarantee. And a meta-heuristic, for me, is a completely different animal. It's not a method, it's not an algorithm. It's more of a set of ideas and concepts that give you guidelines to develop a heuristic optimization algorithm. Right? For me, it makes no sense to say, I have developed a meta-heuristic for the vehicle routing problem with time windows, because you don't develop meta-heuristics for specific problems. Meta-heuristics are generic, right? So, for example, a meta-heuristic is taboo search, with the idea of escaping local optima by using memory structures, long-term memory, short-term memory, taboo lists, frequency memory, whatever. That is a meta-heuristic. And let's say the taboo search by Eric Taillard, published in 1997 for the vehicle routing problem, that is a heuristic. So that's no longer a meta-heuristic. The meta part is no more present. It's a specific heuristic for a specific problem. So a heuristic is an algorithm. A meta-heuristic is not an algorithm. It's a concept. Right? Okay. Okay, so I was talking about how we tried to find a way to be a bit more systematic about designing heuristics. We applied those ideas to the vehicle routing problem, and we were actually very successful in doing that. And by we, I mean myself, but especially my PhD student, Florian Arnold, who has done most of the heavy labor here, doing programming and the development and things like that. So, many thanks also to him. I don't know if he's watching, Florian. He should be. Okay. Sorry, I don't need to explain the vehicle routing problem anymore, but I will anyway. So we have a central, or not so central depot. We have a set of customers. The customers have a known demand. And there's a lot of vehicles here at the depot, and they need to visit those customers. And you can only visit so many customers in a route that the total capacity of the vehicle is not exceeded by the demand you pick up in that vehicle. Simple capacitated vehicle routing problem. And the aim is to minimize the total route length or cost or any measure of the route length. Right? It's one of the most studied problems in OR. Michael has talked about it a lot. There's lots of papers being published, like hundreds of thousands at this moment. Every year we see tens of thousands new entries in Google Scholar. And most of those, or at least a lot of those, are on heuristics for the vehicle routing problem. So there's a lot of interest in studying this problem. But it's not only theoretically relevant, it's also very practically relevant. As you can see from here, this is an example of real production software to solve vehicle routing problems. Not just the simple capacitated vehicle routing problems, but any variant of that problem. And that's a big difference between vehicle routing in practice and vehicle routing in theory, in academics. In the academic world, we develop an algorithm that works for one specific problem. We spend a lot of time getting the most out of our algorithms so that it works for that specific problem. In practice, you don't have that luxury. You need to have some software, something that works for many, many different problems. Because every customer you get will have a slightly different problem. Right? This customer has all sorts of different vehicles. Some vehicles cannot visit some customers. Some vehicles cannot traverse some paths. Some trucks are too large to run along some roads, for example. There's customers who want you to also minimize the risk because they're transporting dangerous materials, for example. Some customers have tight time windows, others have loose time windows, etc., etc., etc. So the list of things that people can, the list of types of routing problems that you need to solve as a company is basically endless. So you need something that is very versatile, that is very flexible, and that can handle many, many different problems. And you need, of course, software like this, which is nice, which has a nice interface, which gets its travel times from some server where the current traffic situation is taken into account, etc. So it's really very demanding too, but on a different level. In theory, we can keep ourselves to one specific problem and try to solve that as well as we can. Even though I think that most of the ideas that we use in heuristics are ultimately also transferable to these problems. The idea of using local search, constructive methods, etc. are also very useful in these practical situations. So as I said, there's a lot of extensions, but it's not only the vehicle routing problem itself which is important. The vehicle routing problem is also part of many other problems in logistics and supply chain design, such as location routing. I need to determine where to put some depots, knowing that from those depots I will start vehicle routes to visit my customers. And one way to do that is to solve the vehicle routing problem as part of the location problem. And you have a location routing problem. Inventory routing, where I determine routes, but at the same time make those routes so that I manage the inventory at my different customers. Right? I visit different cafes with different types of beer, and I make sure that every cafe has, at every point in time, all the types of beer in sufficient stock. So there's an inventory management problem combined with a vehicle routing problem. Or the school bus routing problem, something I solved with my colleague Mark. You determine routes to pick up students, but you also need to tell the students which stop they need to go to. It's you, the bus company, that can assign the students to stops as long as they're within a certain radius of their house. And by doing that in an efficient way, by taking that decision in an efficient way, you can make better routes. So those problems are also combined, etc., etc., etc. So I can go on and on. And all of these problems, like all of the variants of the simple vehicle routing problem, but also these multi-layered, multi-level problems, rely on an effective algorithm for the vehicle routing problem. They all need a very good algorithm for that. So what's the state of the art in vehicle routing problem? It's basically your methods, which I, as I said, I call iterated hacking. You basically add local search operators or constructive operators, whichever bears your preference, and you add them until it works. You start with simple insert, remove a customer from somewhere, insert it somewhere else. Okay, that doesn't work, maybe 2 opt. That still doesn't work, try to swap customers, etc. And you continue that process until it works. Or you construct solutions in different ways. You try to nearest neighbor construction heuristic or some other construction heuristics, etc. So you end up with something which is which we could either call variable neighborhood search if you use local search heuristics, or large neighborhood search if you use constructive heuristics. So large neighborhood search, as you know, you alternate between constructing the solution and then destroying part of the solution. In many cases, you would try to fit that in some kind of meta-heuristic framework, or you would have started from some meta-heuristic thing. Many people have their own pet meta-heuristic, in some cases literally pet if you're into, I don't know, dog-based optimization or dolphin search or cuckoos or ants or lions, clouds, water drops, musicians, etc. If your pet framework, which is nice. But in itself, that doesn't really work. So you would still add these local search operators or these constructive operators until it works. And then you have something that works. Right? In most cases, however, if you start from harmony search, you would still call the end result of your heuristic a harmony search for the weak routing problem, even though it has, I don't know, 10 different local search operators in it, and the harmony search in itself doesn't really do that much. So the meta-heuristic framework will still be your unique selling point. Oh, I have a new algorithm because mine is a harmony search, and the previous one was a cloud-based optimization, and there's the bio-ecosystem optimization or the football league optimization, whatever. It really doesn't matter that much. You need these local searches or these constructive operators, otherwise it just won't work. What you tend to get then, I think, might be something like this. Sorry for the picture. So you'd have a car. It would have some really expensive tires, a very nice engine of local search operators. Let's make the metaphor here. These are the local search operators. You would add like a rocket engine and a helicopter screw and then a boat screw on it. Okay, and then put your favorite animal behind the steering wheel. In this case, this would be a raccoon-based optimization for the weak routing problem. Right? But what works? What is really necessary for this algorithm to achieve that performance? Is it the raccoon behind the steering wheel, or is it the engine of local search operators? If you deconstruct most weak routing algorithms in the literature, you'd find it's here, that's in these local search operators, that the actual optimization is done. There's lots of algorithms that have all these different parts, but there's almost no algorithm that doesn't have a core of local search operators, even though it's called a genetic algorithm or whatever. So the state of the art is use as many local search or constructive operators as you can find, as you want, as you feel like programming, and then do that until it works. Okay, let's look at a few of those. Famous operators like two-opt, where you try to exchange two edges until you find an improvement. Complexity is quadratic, so in the weak routing problem, if you have n customers, you have something like n edges, approximately. If you need to check all the swaps, all the removes of both edges, and then reinsertions, you end up with something which is quadratic. 3-opt, very original extension of 2-opt, where you try to swap 3 edges. Comes then a cubic neighborhood. You could try 4-opt. Most people don't because it's too complicated. You could. insert and relocate. You take a customer from somewhere in the solution and insert it somewhere else in the solution. And again, you end up with something quadratic, because there's n customers and n positions to locate them in. So if you want to try all of those combinations, it's n squared. Swap, exchange two customers. Crossover, you exchange the ends of two routes. So one route becomes the next, etc. And then something more complicated, which is still used, cross-exchange, where you exchange any sequence of customers between any two routes. This is to O to n to the power 4. Why? Because in each of these sequences, you need to select the first customer, the last customer. You need to do that twice, so that's n to the power 4. Cross-exchange is a lot more powerful than all of the others. You can search for a lot more moves, but it's also a lot more time-consuming, a lot more complicated. The complexity is much higher. And that shows, of course, in the speed with which to execute, with which you will execute cross-exchange. So you will find better improvements, but it will be slower. And that is a general thing that we have about these neighborhoods. The more complicated the neighborhood becomes, the more complex the local search operator becomes, the slower it will be. Right? So there's some kind of inverse correlation between the power of a local search operator and the speed. So we tend to stick with the fast ones. Right? To opt, remove insert, swap, etc. Those are the ones you always see coming back. Okay? These local search operators do not only make sense because they actually improve the solution, they also make sense in a way because they visually improve the solution. And this is important in commercial software. You don't want the commercial software to find a solution that any 12-year-old can improve by hand, because of course the commercial software is very expensive. You don't want the manager to go home and show his son, look what the software can do. And then the son says, yeah, but Dad, if you do it like this, it's much better. Yeah, okay, I just paid 50,000 euro for this. That's not... Those guys are going to get an angry phone call in the next morning. So if you have these simple operators, which make very much sense to us, of course. Like this is faster than this, so okay, you swap it. Makes a lot of sense. Same here. If you take this sequence of two nodes and you insert them in the next route, it's better. You can see it. So that makes sense. Or here, a 2-up move. This is obviously better than that. So that makes a lot of sense. It's an extra reason why it's implemented in commercial software solvers. And you need all of them because, let's say, this one, this bad solution, crossing of edges, you cannot improve using this move. Well, you can, but not in a series of improving moves. There is no way that you can move from here to there using the swapping of two customers while every time getting a better solution. Right? So if you only have this move and you find this structure in your solution, you either don't improve it or you need to rely on luck in your diversification operator, for example. You destroy part of the solution and then in the destroyed solution you end up with something which is not this. That can also happen. But that's not so efficient. So that's also a reason why you implement many local search operators. Because one local search operator is very myopic, only has a very limited view on the solution. And if you put many of them at the same time in place, you're able to improve many more deficiencies of the solution than using only one. Okay, so what's the state of the art in solving VK routing problems. These are a number of algorithms which we put in a graph. This is the average gap to the optimal solution, and this is the total CPU time. And as you would expect, there is some kind of a Pareto front here of equivalent performance, let's say. Heuristics that either have a better gap, more towards here, or a lower computation time. So it's more or less of a Pareto frontier. Faster algorithms have bigger gaps, slower algorithms have smaller gaps. That makes sense, of course. We do, however, seem to be stuck at around 1,000 customers. That's what we can solve using heuristics. In principle, we can solve problems that are arbitrarily large, but then it will take more time than you can consider reasonable. We're going to look at this from a more or less practical perspective, where I would say something like an hour, 2 hours, 3 hours of computation time is more or less the maximum you can get. This is, VK routing problems are things, in practice you can expect the planner to press a button and then come back in an hour or two to see the solution at most, but you cannot expect him to wait for 11 years before this problem is solved, of course. So in terms of solving problems of many customers, 1,000 customers approximately seems to be where we are now. Solving more customers is problematic. Here you see the performance of two of these state-of-the-art metaheuristics, no, I should say heuristics, sorry, in VK routing. Iterated local search and a hybrid genetic algorithm. And as you see, for a few hundred customers, 200 customers, 400, 500, 600, we are, say, within 100 minutes. But then as we move to 800, 1000, we're at like 700 minutes, 800 minutes. That's more than a day of computation time. And of course, this function goes steeply up, so if you add 1,000 customers, be prepared to wait for a very long time. Okay, that's state of the art. Now some problems have many more customers than 1,000. Things like parcel delivery, we're talking about tens of thousands of customers from a single depot. Can we do that? Can we solve with the same performance, or not much worse than the 1,000 customer instances? Can we solve those 30,000 customers, 20,000 customer instances? Some garbage collection instances are that large. 10,000, 20,000, 30,000 customers. So can we reach the same performance with instances that are an order of magnitude larger? That's the question we asked ourselves. So we decided to try some fresh ideas to do this. 3 of them, actually. One is to not use this, let's say, carpet bombing approach, where you basically throw everything you have at the problem, all of the heuristics you can think of, put them in the bag, shake the bag, and see whether a good solution comes out. Not that approach. We decided to try a set of selected, specifically selected operators that are complementary, in the sense that they don't try to solve the same issue in the solution. Okay. We chose rather complicated heuristics for that, so the more involved local search operators, which are too complicated to solve these large problems. But then we tried to make them more efficient. And we did that first by focusing them on the problematic parts of the solution. And for that we tried to learn by machine learning which parts of the solution are problematic, are We'll talk about that a bit later. And then we went even further. So we focused the heuristic on a specific part of the solution, and then we heavily restrict its use to those parts that we assume might yield an improvement. Right? That's pruning. We heavily prune these heuristics to make them much more efficient. So we get a heuristic based on local search operators that are complementary. Okay? I already said this, so the basic state-of-the-art idea is that either you use something which can be called multiple neighborhood search, lots of local search operators, or lots of constructive heuristics, and the general sentiment is that it doesn't hurt to try. So if you have an extra heuristic that you can think of, an extra local search operator that you can think of, just put it in there. If it doesn't hurt, then if it doesn't help, then it doesn't hurt. Okay? But there is an overhead, of course, for every operator that you implement. They still have to be executed. They have to search the solution for possible improvements, etc. Moreover, you're going to be, many operators have at least slightly overlapping domains. So they're going to be trying to do the same thing in many different ways. And the problem, of course, is that powerful operators tend to be slow. So if we want power, then we need to do something about that. But an important remark here is that this is based on the fact that you expect to be searching the entire space of the solution. And by doing some pruning, you don't need to do that, as I will show you. Okay, so here's our heuristic. It consists almost entirely of 3 local search operators. One that tries to optimize one single route. Another one that tries to optimize 2 routes at the same time. And another one for optimizing more than 2 routes. So in this sense, they are completely complementary. There's no or very little overlap between the ranges of these operators. For one route, we chose the Lin Kernighan heuristic. Lin Kernighan is not really a heuristic, but more of a family of heuristic, but generally considered the most powerful set of heuristics for the traveling salesman problem, because of course, if you only consider a single route, it becomes a traveling salesman problem in a capacitated vehicle. For 2 routes, we chose the cross-exchange operator that I told you about. And for more than 2 routes, we chose a relocation chain. I will explain later. Of course, every operator is very powerful. Lin Kernighan is the most powerful heuristic for the TSP. Cross-exchange is very complex and so very powerful for 2 routes, and ejection chains for more than 2 routes. But they're also very complex. And we need to do something about that, or otherwise it's not going to work. So the Lin Kernighan heuristic basically solves a TSP by exchanging edges. So it's more or less a generalization of 2-opt, 3-opt, 4-opt, 5-opt, etc. The thing is that it uses an intelligent way to select the number of edges to remove and the number of edges to insert. It's more or less it dynamically searches the space of edge exchanges. If you're interested, I refer you to the papers on this heuristic. They're much too involved to explain in a short period of time. Just let's say they exchange edges in a very intelligent way. And they're generally considered very powerful. Okay. Now, in vehicle routing problems, the routes are generally much smaller than the typical TSPs that we see. Right? If you have 30,000 customers and 300 vehicles, you still have only 100 customers per route. which for Lin Kernighan is really a piece of cake. Really very easy. So we can even be a bit more aggressive in the way that the Lin Kernighan heuristic is implemented. Lin Kernighan most of the time tries to use a first improving approach. If it finds an improvement, it immediately executes it. In our implementation, we could do steepest descent. So try all of the possible improvements and take the best one, which worked for us slightly better. For two roots, we use a cross-exchange operator. I told you it exchanges basically any subroute from one tour with any other subroute of another tour. And complexity is O to the power n of 4. And if you want to keep that complexity within bounds, you best restrict the length of those subtours. Otherwise, it's very nasty. And then for three routes, we use a relocation chain. What's that? Well, basically, at one point, you eject a node from a route, and you insert it in another route. Insert it here, for example. And at that point, for example, this route has a capacity problem. Well, you can eject another node from that route and insert that in a new route. And do that. Right? So a route has, for example, a capacity problem, too many customers. You remove one from it, put it in another route. Now that route has a capacity problem. You remove a node from that route until you have no more capacity problems. Okay. Of course, this is complex. There's a number of customers here, n times n times n, etc. And this can go on and on and on, depending on the length. So you best also restrict here the depth of the chain. You cannot do a length of 20 ejection chain. That doesn't work. It's much too complicated. But these three operators are complementary. One is for one route, one is for two routes, one is for more than two routes. Do they work well if you compare them to the more traditional operators? Yes. Well, here you see the performance of 2-opt to improve a single route, and then relocate, swap, and or exchange to improve two routes. Okay, that's the performance. This graph is for Lin Kernighan to improve one route and cross-exchange for two routes. You see it's already a lot better. And if you then add the relocation chain, the performance is even better. So for the same amount of time, you find a lot better solutions. So that shows that this is a promising approach. We did a lot of experiments here, but this is maybe a summary of those. Okay, so these three, of course, need to be combined in some way, and we chose a simple meta-heuristic framework called guided local search. And that guided part is also part of the second idea that I will be talking about. So the idea of the guided local search is that we're going to be penalizing bad edges. So an edge that we consider to be bad for the solution, maybe because it's too long, we're going to put an extra penalty on it, so the searches will remove it with some preference. The basic meta-heuristic works as follows. So we penalize some edge that we consider bad for the solution, and then we do local search starting from that bad edge. So we say this edge is the worst in our solution, and now we remove that edge, and then we apply the local search operators to basically, we tell the local search operators, you remove that edge first, and then do your work. You know? And that we repeat. It's very simple. So you take the worst edge of your solution and tell the local search operators, remove that edge and continue with your search. and those edges are penalized, so we make them a little bit worse. Now this opens the question, what is a bad edge? Which edges should we penalize? And that brings me to idea number 2, in which we are going to learn what a bad edge is. Learn in the sense of machine learning. So let's say you have these two solutions. This one is a very, very good solution to the same problem, by the way. This is a very, very good solution. It's 0.14% over optimal. This is a not so good solution. It's 2% over optimal. What's the difference between those two? Why is this one close to optimal and this one not so close to optimal? Is there some way in which only by looking at the solutions, so only looking at the solutions and not at the objective function values? It's easy to see that this one is better because of the value of the objective function, of course. But without looking at the objective function, can we tell that this solution is better than that one without looking at the objective function? Yeah. So another way to put this is there a relationship between the characteristics of a solution, the characteristics of an instance, because that also might have an influence on what we're going to learn, and the quality of a solution? Are there properties of this solution that make it better than that? Properties other than the value of the objective function. Okay. That means basically that you're going to be acquiring problem-specific information on the VRP. So you're going to learn something about what constitutes a good solution in the VRP. If you're building a solution, what do you want to focus on? There's a lot of problem-specific, or there's a lot of reference in the literature to problem-specific information. So you regularly find things like this. You need to make use of all the problem-specific information that you can get, or if you use a perturbation, please incorporate problem-specific information. You need to exploit problem-specific information, etc. So you regularly see quotes like this, but what's meant with problem-specific information is very rarely specified. So that's something we wanted to contribute a bit to. It's very problem-specific, of course. In the TSP, we know that the optimal solution has no crosses. They don't occur because it's very easy to improve a solution if it has a cross. But in a VRP, that's not the case. So you cannot say that if you have intersecting edges in a VRP, that necessarily is a bad thing. It might be, but you don't know. So it's problem specific. You need to learn it. And how do we learn it? Well, this was our idea. If you take a random instance, and of that random instance, you have a solution which is very close to optimal. Right? We call it O. It's optimal or at least very close. And you have another solution which is not so close to optimal. Right? So a good solution and a bad solution, or optimal and non-optimal. Right? And if you then collect the number of characteristics about both that instance and both solutions, then maybe machine learning techniques can tell you a bit about which characteristics actually distinguish the good solution from the bad solution. Maybe you can predict from things like the number of intersections or the average width. We'll tell you later what we mean by that, or the average width of the edges in the solution. Maybe from those characteristics you can predict whether a solution will be good or bad. Right? And if you've learned something, like for example, let's assume hypothetically that the number of intersections is very predictive of the quality of a solution. If you have more intersections, the solution is going to be much worse. If you know that, then you know you should focus on removing intersections from your solution. Right? Makes sense? So we gather all this data, and then we try to predict. We give an algorithm, say, okay, we have an instance and this solution. Tell me whether you think it will belong to the class O, optimal solutions, or the class N, not optimal solutions. And from that you can extract rules and knowledge about the problem. So we generated lots and lots of different instances, relatively small ones, up to 100 customers. We have two sizes, 20 to 50 customers, 70 to 100 customers. The depot was either put in the center or somewhere near the edge. Maybe that makes a difference. The demand was either all the same for all customers, or it varied between 1 and 10. And the small generally have between 3 and 6 routes. The larger ones have 6 to 10 routes. Well, that's generated thousands and thousands of instances. And for each of those instances, we generated a very good solution and a not so good solution. Okay. The very good solution was generated by our own heuristic. So this is a bit of a bootstrapping, recursive thing. So we design a heuristic, but we then use it to design our own never mind. So our own heuristic was very good, so we used that to generate a near optimal solutions. On average, on these famous instances, we get 0.2% gap, which is very good. So that's all right. And then we needed, of course, a solution which is not so good. How do you do that? And of course, you need to make sure that the results you get tell you something about the solution. Why is a solution not so good? And don't tell you something about the heuristic that you use to generate that solution. If a heuristic generates a solution which is bad in a very specific way to that heuristic, then you haven't learned so much. You need to find why a solution is bad because of that solution, not because of the way you generate it, if I make myself clear. So for that we use two different heuristics to trap that. One was, again, our own heuristic, but a weak version. I mean, basically we stopped it when we reached a solution of 2% or 4% from the best one we found. Just cut it short. And the second heuristic was a modified Clark and Wright heuristic that we found in an interesting paper, which I will tell you about now. Both of these heuristics, therefore, are rather weak. You wouldn't call them good heuristics for the weak routing problem. The improved Clark and Wright algorithm, by the way, this is a bit of an intermezzo, was found in this paper, published by these guys in a Thai journal of the Thai Science Society. So basically, I think you are aware of the Clark and Wright algorithm, or at least you should be. So basically, you put every customer in its own route, and then you start merging routes in order to save travel distance. And there's a set of rules that tell you whether you can or cannot merge two routes. So you greedily maximize the savings from merging routes. So it's a greedy heuristic. Problem with that, it only generates one solution, and if you repeat it 10,000 times, it gives you the same solution 10,000 times. So what these guys did is very simple. They randomized a little bit the savings list. And so instead of taking the best saving and then the second best and then the third best, they randomized that a bit. They take the third and then the first and then the second and then the fifth and then the fourth. Okay. That is random, so you can repeat it. They do it 10,000 times and then take the best solution. Of course, it's going to be better than the standard Clark and Wright. going to be better than the standard Clark and Wright, of course, because that tends to happen if you slightly randomize a greedy algorithm and then repeat it many, many times. But the performance of their heuristic is simply unbelievable. It's basically one of the best heuristics for the VRP in existence in the whole literature. And if you've developed an algorithm for the VRP, like I did, you will frown your eyebrows and say, that sounds too good to be true. Right? So you have something that is so very, very simple, and it beats everything that is much more complicated and much more involved. That's too good to be true. It turned out to be actually too good to be true in the sense that it wasn't true, because we re-implemented their heuristic and found that the actual results of that improved Clark and Wright, even though it's a bit better than the actual Clark and Wright, was much, much worse than they put in their paper. In fact, in all of the instances that we solved, we almost never found their results. We never were better than them, and almost always worse. So I think you can say that they were cheating, and they just took the results from another paper, and anyway, not very honest. So if you want to read all about this detective in search of was, by the way, not a trivial exercise to actually write this paper, because of course if you want to demonstrate that some people are doing something wrong, you have to make sure that you don't make any mistakes yourself. So to do that, we re-implemented their algorithm twice independently until the results matched statistically, because both stochastic algorithms, you want to make sure that the results are, of course, the same for each of those implementations. It took months before we could do that, months of tweaking and turning. And it turns out that there's really, it's an important lesson. The description of an algorithm you read in a paper is very, very far from being exact enough to allow you to re-implement it. And the actual results of an algorithm depend on really trivial things, like which exact sorting algorithm do you use, and how are the ties treated in that sorting algorithm. You saw, right? If you handle your ties slightly different way, completely different results. You have smaller than, I have smaller than or equal, even though we're dealing with real numbers, and that shouldn't matter. Completely different results. So those tiny details of implementation actually matter a lot in the results that we present. Without all of those details, results can never be truly replicated, which is why I always tell my PhD students, you need to share your source code. You need to put your source code somewhere so that people can actually replicate your results. They could never do it from the description of the algorithm that's in the paper. The only way to do that is by actually giving people access to the source code. But that was a bit of a sidestep, so let's go back to the methodology. So we've generated different instances. We have two solutions. One is near optimal and one is non-optimal, with two different heuristics here. So we are sure that the results are not a result of the heuristics that we use. And then we generate a number of characteristics of these solutions. Which characteristics? The intersections. How many intersections does a solution have? What's the longest distance in, what's the longest distance in the roots that you can find? What's the longest edge in the roots? What's the distance between the depot and the customers that are connected to it in the solutions? Should you go from the depot to a close customer, or should you move to a customer that is further? How far are the routes from each other? Are they really separated? There are long distances between their centers of gravity. or are they close to each other? Don't really mind the formulas, just intuitive. What's the width of a route? Width is something like how wide the route is measured to the line that goes between the depot and the center of gravity of the route. I have a picture later. Or how wide is the route in terms of the radius of the different customers. Compactness of the route, which is something like an average width of the customers. Compactness by radian. The depth. It's the furthest customer. What's the average depth? Numbers of customers per route. Are they all the same, or do they vary a lot, etc.? So we tried a lot of these metrics. Here you see them again. So number of intersections. What's the longest edges you can find in the different routes? What's the length of the first edges that connect customers to the depot? What's the distances between the routes, between the centers of gravity of the routes? What about the number of customers? Are the routes equally spaced or not? And then the depth, so what's the furthest customer away from the depot in the route? The width, so basically if you draw the route, how wide is it? Same for this seen as an angle, and compactness is something like the average width of the customers. So all of these might influence the solution quality, we don't know yet. And of course all of these are problem-specific metrics. So you cannot use these metrics for, I don't know, the facility location problem or for the knapsack problem, whatever. That doesn't work. So it only works for the capacitated VR. Okay, so we generate lots of solutions, some near optimal, some non-optimal. We see that we need to normalize, because even things that are very similar, solutions or instances that are very similar in terms of number of customers, size of the space on which you calculate that, have very different ranges of these metrics. So we normalize them, and then we add also a number of instance characteristics, because these conclusions might not be valid for all instances. Maybe if you have a lot of customers, then this is a valid conclusion about the quality of solutions, etc. So you see a number of instance characteristics that we also add. Okay? So now we are here. We have calculated all of those characteristics for the different instances and for the different solutions. And now we try to predict or train a machine learning algorithm to see whether, based on those instance characteristics and those solution characteristics, it can predict whether a solution is near optimal or non-optimal. Okay? We use support vector machines. I'm not a machine learning specialist, so I'm going to just show this ugly picture. A support vector machine basically tries to draw a hyperplane that, as best as possible, separates two groups. If you have the optimal solutions and the non-optimal solutions, basically tries to separate those two groups by a hyperplane, and then the characteristics of that hyperplane tell you based on what you have made that decision. And here are the results. Let's move immediately here to the largest numbers. Basically, if you have a 4% gap between optimal and non-optimal, and the instance is large, right? So this is the 70 to 100 customer class, then the algorithm can predict almost with certainty whether a solution will be near optimal or non-optimal, just by looking at those things that I showed you, like the width and the depth and the number of intersections, etc. And this doesn't know anything about the solution quality of the optimal solution. Right? So I give you a solution, I tell you it has so many customers, the width of the edges is this is the depth of the edges, these are the number of intersections, and Based on that, it tells you, okay, I predict that this solution is optimal, and it can do that with a very, very high accuracy. Okay? That's nice, but we still haven't learned much useful, because we need to somehow translate that into something that we can use in our algorithm. Let's look at the details. These are the effects that, or the individual prediction accuracies of the different characteristics, where it's larger than 55% individual prediction accuracy for the 2% and the 4% gap. And what do we see coming back? S8 and S7, which is the compactness, the width of the edges, in average width, and also the maximum width, S5 and S6. Intersections seem to count, and the length of the edges from the depot also seems to have some effect. But most importantly, I think 5, 6, 7, and 8 are all about the width of the edges. So if you have a root, it seems that if you have a root, what you don't want is edges that are wide. If you have a root like this, seems to be better than a root which goes like this, something like this. Right? And that is something that we can use. You can see how wide an edge is. Something we can use in our algorithm. We can measure that. And we're going to do that. So we're going to look at those wide edges, also at deep edges, and long edges. That also makes sense, of course. We don't want long edges. Penalize them, and then use it in local search. Okay, so we have these local search heuristics. We have learned something about where they should focus. I do that. So the width of an edge is this. It's basically the length of that edge, but measured along an axis which is perpendicular to the axis that connects the depot to the center of gravity of the root. This is the width of an edge. The width of this edge will be something like this, etc. And you don't want that. You don't want wide edges. You want a solution to go up and down and not like this. That's what we learned. Okay? This, I'm going to skip it. So, okay. Now we still need to make our local search heuristics much more efficient. How are we going to do that? By pruning, by focusing them on specific parts of the solution space where you expect improvement. If your solution is reasonably well, if you have a reasonably good solution, you don't expect that you can still improve it by switching or by swapping customers which are on completely different sides of the area in which the routing is taking place. If the solution is reasonably well, there will never be, that just doesn't exist. So it makes sense to only try to operate within a certain limited part of the area. Yes, we're going to. And that really can improve the performance of the local search operators, especially those complicated ones, because they have a very high complexity. Like if you try to relocate each customer in every possible position, that's n squared. But if you say I limit myself to repositioning it in only A positions, A is a fixed number, 5, 10, 50, I don't know, then the complexity basically reduces because A is now a fixed number, and it's no longer a function of the number of customers. So it's A times n. And if you already know which customer you want to relocate, then basically it becomes constant. If you say, for some reason, customer 1 is the one I'm going to relocate, and I'm only going to relocate it in 5 positions, then it's constant, the execution of that heuristic. Of course, it's going to hurt your performance because you're checking less and less options. So hopefully you don't restrict yourself too much, and you manage to still get the same performance with much less computing power. So that's the idea we did. For each of the heuristic, we went to see how can we restrict the range, the reach of this local search heuristic without giving in to performance. Lin Kernighan was not really a problem. It was already very efficient. We restrict the Lin Kernighan heuristic to the 10 nearest neighbors. So we never swap arcs that are between customers that are more than, in the list of neighbors, more than 10 spots away. That's a restriction. And we never go beyond 4 opt. But if we do that, we still have a very efficient Lin Kernighan. Here, the cross exchange. The cross exchange always starts from the most penalized edge. Yeah. And then everything it does, it searches only for new edges within the 30 nearest neighbors of the customer that you chose. So you cut the edge here, you take this customer for example, and then you only look for connections between one of the 30 nearest neighbors to these customers. Remember, I was talking about 10,000, 20,000, 30,000 customer instances, so this is a severe restriction. I'm restricting it by a factor of 1,000, for example. And also, you don't look for exchanges where the subroute is longer than 100 customers. That's still long, but so this considerably reduces the complexity of this neighborhood without giving in too much to quality. Relocation chain. First of all, we don't try chains which are longer than 2 because each chain adds an extra level of complexity. We restrict again to 30 nearest neighbors, and again we start from the most penalized edge. So this edge or that edge, we remove it, take one of the nodes that is adjacent to that edge and try to insert it in a route, but in such a way that you don't go further than the 30 nearest neighbors of that edge. Yep. So again, a lot simpler than, or a lot less computational complexity. Here is the effect of the tightness of pruning. If you C is the number of nearest neighbors with which you, so how far you look in the solution space. If you try to put a new edge between a customer and a customer that is, let's say, the 200th customer in that list of nearest customer, then C would be 200. If you restrict it to, let's say, if you are too loose, let's say C is 100, you can make exchanges up to the 100 nearest neighbor and the 100 nearest customer, then the performance is clearly not very good. And if you tighten it up, it gets better and better and better. You can also make it too tight. If you restrict it to 15 nearest customer, again the performance suffers a bit. So 15 is too tight, you don't check enough options. 100 is too loose, you check too many options, lose too much time. Something like 50 or 30 seems to be a good compromise here. To show that pruning really makes sense. Okay, here you see another rationale for those numbers without doing actually any effect. You take a number of really high quality solutions and then see which customers are connected. So you take this customer and see, is it connected to its closest neighbor, its second closest, its third closest, etc. And you do that for all customers. Then you have so like a distribution of connection length. The black bars are 95% and the error bars here are 99%. So in these high quality solutions, 95% of all customers are connected to their something less than their 50th neighbor, 40th neighbor. In this case, it's even the 20th neighbor. So it really doesn't make any sense to try to make a swap between a customer, or to try to do something which would connect a customer to its 200th nearest neighbor. That doesn't make any sense. And it makes a lot of sense not to do it because you severely restrict the necessary computation time. Okay? It also helps you solve some memory issues because, of course, if you have 10,000 customers and you need a full distance matrix, 100 million, that's already a lot of memory. It takes a lot of time to fill it up. And of course, it increases quadratically. So it's not only good for the heuristics, it's also good for memory management. Okay, and then this is the complete algorithm. See, it's very simple. You construct an initial solution. We use a simple clock and write. And then you repeat our main loop. The main loop repeats guided local search and some global optimization. Okay, so the guided local search penalizes the edge. So it takes the worst edge based on a function of the width, of the depth, etc. If you just take the width, it helps a lot. It's already very good. And P here in this function is the number of times this edge has been penalized, just to make sure that you don't always penalize the same edge again and again and again. So you penalize it once, but then you give it somehow a chance to redeem itself and rise in your list of, or at least drop in the list of edges that you want to remove for sure. Okay, so the edge that scores the worst on this index B, is called W. That edge is removed for sure, and the local searches start from that edge. Okay, and you use local search using this penalized edges as the criteria. So you use the edge penalization as the objective function. And then every now and then, you forget about the edge penalization, you use the normal local search, and you apply the local searches on the entire solution. So without going first towards the penalized edge. It's like a global optimization. That takes a lot of time, so you try to avoid doing it too often. But sometimes it helps. Okay. One extra advantage is that it's completely deterministic. Okay, that's nice. Again, if you are selling software and it costs 50,000 euro, and the guy presses the button and it finds a solution, but his colleague comes, he presses the same button and the solution is much worse, and they spend an hour. Oh, I don't know what happened. And they spend an hour trying to get that first solution again. Okay, they're not going to be happy. Being a deterministic is nice. It's good. It's a good property. I think we're also too kind on stochastic algorithms. We allow people to say, I run my algorithm 20 times and here is my best solution. I say, no. Your algorithm is running your thing. Yeah, your algorithm is running that thing 20 times and then reporting the solution. That's not fair. It's like in statistics. When do we reject a null hypothesis? When we're 95% sure that's what we should do. I think we should move to a similar way of reporting the results. If the algorithm is stochastic, you run it 20 times and give me the second worst solution, the 95th percentile. You are 95% sure it's going to be better than this. That's how I would report it, but okay. This is deterministic, so we don't have to do that. Movie time. This might be slightly, oh no, sorry, this computer might be slightly boring, but anyway. So this is how it works. What you will see is edges flashing. That's where we focus. This is the global optimization, and now every time you see an edge flashing red, is basically the worst edge being penalized, and then now and then a part of the solution is optimized. This one is about 1,000, I think. Okay. It's very hypnotic. You are. Okay. I think you get the picture. Okay. So what is the results? We need a few tables of results or graphs of results. Here is the graph I showed you of the initial of the state-of-the-art algorithms. Here's the performance of our algorithm. So to achieve almost the same performance as those other algorithms, we could say we're slightly worse, but much faster, and there's much more a straight line than the other ones that go steep. Basically, we're here. If you see us, the average gap for different computation times. So if we run it a bit longer, we're here. If we do it really fast, we're there. Anyway, see, we kind of dominate this Pareto front. So, very good result. Very large instances, up to 12,000 customers. There's only one algorithm in the literature that has tackled some very large instances. And yeah, we basically wiped the floor with them, to put it nicely. So much better in much better in the same amount of time, and only slightly worse in faster computing times. Better. This algorithm wasn't very good, so it's maybe not so difficult to beat. So that if you need to be able to tackle these very large instances, and we get solutions which basically too large to show. 10,000 customers, 20,000 customers, or here 30,000 customers. Where you see this is Flanders. The depot is here. This is where I live, Antwerp, and this is but that doesn't matter at all. But okay. So anyway, and this is a zoom of the Brussels region, so you really see how fine-grained. Okay, of course, you have no idea whether this is a good solution or not, but it's just nice graphs. We got an unexpected benchmark before actually this was published. Mr. Kenneth Sörensen from Denmark. He's the H of the LKH, Lin Kernighan Heuristic implementation of the Lin Kernighan Heuristic. Very famous guy. He had a solver that could also solve vehicle routing problem instances, LKH3, and he got our instances and tried to solve them. And he found tours that are better than ours. Okay, very nice. Good for him. Only what's still good for us is that he needed a month of computation time to get them, whereas we reach ours in just an hour or so. And I think that was somehow nice. Okay, within a short amount of time we can find something. These are certain to be very good results. So ours are only slightly worse, but much faster. Here you see some of them. So up to 30,000 customers. The gaps are actually small. And ours, there's no computation times here, but ours are certainly much faster. Okay, So to conclude, I said designing heuristics the modern way, it's more of an alternative towards the implement everything you know and then hope it works idea. So take a set of, so how does it work? Step one, you take a set of local search heuristics. You take some powerful ones, strong ones, maybe even derived from exact methods. You could do that. Make sure they're complementary, so they don't. So you basically get the whole range of different changes you want to make. You can try to make them efficient by learning, giving them some knowledge about what a good solution is compared to a bad solution. Maybe use the way I showed you. And then make them much more efficient through heavy heuristic pruning where you can. This makes a lot of sense for solving really, really large instances. So, I think I can say it works for a capacitated vehicle routing problem. I have no idea whether it will work, the same ideas, for other problems. So this is my challenge to you. If you have a nice problem to solve, maybe think of the ideas that I gave you here, try it out, and let me know if it works. If it doesn't work, also let me know. Okay, but, no. Yeah, that was it. Thank you very much.
Very much. We have time for some question, maybe 2 questions.
And that, in fact, that's what my question. I mean, is can be used for another kind of problems, a part of vehicle routing problems, and additionally, how can include the stochastic behavior in local search? Thank you.
Well, yes, I think you can use it for other problems. The idea is very generic. Basically, instead of trying to use a lot of simple operators and just implement them standards, take a few that are a bit more complicated and put some more effort into making them efficient. Maybe by learning about the properties of the good solutions, but especially also by not making them check things that you know in advance will not work. So I think it, for sure, it will also work for other problems. For the vehicle routing problem, it worked really, really well. So I'm not sure that we will see the same thing for other problems, but okay, for the vehicle routing problem, it worked really well. In terms of the stochastic behavior of some local search heuristics, I think that is something which is in a sense unrelated. Whether this works in a stochastic way or in a deterministic way is not directly related to the ideas that I presented here. I don't see why it wouldn't work for stochastic algorithms as well. This one is deterministic, but we might as well have implemented the stochastic version too. What we did try to do was to make sure that everything we implement makes the solution better. Right? So only do things that you know are going to improve the solution. That was, so there's no random big moves here or things like that. That makes the solution worse, and then hope that by luck you will be able to reach a better solution. So as little as possible, we try to rely on luck and chance to get better solutions, and that seemed to have worked here.
We have time for last question, maybe. Yes.
Thank you very much for your presentation. The pruning part of the local search, is it dynamic or static? I mean, is it always 50 closest, or from time to time 50, 60, 70, then come back to 50?
I was a bit afraid you would ask that question. It's static, but it's not the same for all instances. In the sense we found that some specific instances, I don't know the details by heart anymore, but it depended basically on the number of customers per route, if that is very large or very small, some other number for the pruning depth worked better or worse. So we have basically two settings of the algorithm, one if we expect large routes and the other if we expect only short routes, which might be a bit cheating to tune your algorithm in an instance specific way, but it's still light, I say. And you could really do it automatically. It's part of the learning strategy in the configuration of the algorithm.
Okay, maybe a last question, the last of the last of the last.
Just one question. Although the three local searches are complementary, I think they are not independent. I mean, do you have to decide something about the order in which you apply them? Thank you.
Yes, I think in our case, the standard orders in which we implemented them worked well, and I don't think we did a lot of experiments to see whether a different order would work better or not. But you are of course right that they are in some way, they're certainly not independent. If operator 1 makes a change, it affects what operator 2 can do. We implemented them in the order that I showed you. That worked, and I don't have the answer to the question whether another order would be better or worse. But that's certainly something that in some cases might be true and might need to be